This is another lecture for Chapter 5, and in this lecture I'll discuss what's called the standard normal distribution and show how to find arbitrary probabilities both using tables and using R. What's called the standard normal distribution. Remember, this curve has different names. It can be called the bell-shaped curve, it can be called a normal curve or normal distribution, it can also be called the Gaussian distribution. Right? But when it has the title standard, it means that the mean is 0 and the standard deviation is 1. Right? And here's a picture of it. Obviously, here's the mean right here in the middle of 0, and you can't tell from this picture, but the standard deviation is 1. This is a very important curve. R can do things in a more arbitrary way, but for the statistics tables, which people used before they had the software, you couldn't have a different set of tables for absolutely every mean and every standard deviation. Instead, there's through a formula, the different bell-shaped curves are transformed into the standard normal distribution, and then those values are stored in the table. Here's the equation for that standard normal distribution curve. This is the equation for any bell-shaped curve, any normal distribution. Alright, but for the standard one, remember the mean is 0 and the standard deviation is 1, so when you substitute those values, you get the equation that looks like this. It's much simpler. Notice it's written with a z, and the reason for that is that the values of the standard normal distribution are often referred to as the z values or the z-scores. That's to keep them straight from all the other different distributions you might have. It sort of sets them apart, so the variable name is changed to z. All of the areas, the typical areas that we talked about in the previous lecture, those still hold true, of course, for the standard normal distribution. So here's your standard normal distribution. You have your mean of 0, I've said it a million times, now you know it, and a standard deviation of 1. Okay, so if you move one standard deviation above the mean, so here's your mean, and it's mean plus one standard deviation, the area here under the curve is 34%. Going down one standard deviation, you have 34%. From 1 to 2 standard deviations above the mean or below the mean, the area is 13.6%. These are the standard ones that we talked about before. So the way to use this standard distribution is to take your y values, that's the values that you have for whatever data that you've collected. Okay, you find the mean for that. So here's your y values. You find the mean and the standard deviation for that curve. So this is all from the data, and you transform them into the z-scores. And the z value for an arbitrary y is y minus mu over sigma. So let's just look at some key points along the normal distribution and see what they turn into for the z distribution. Here's the general formula right here. Well, let me put it in yellow. Okay, this part's the general formula right here. Now, if you want to change the mean, so set y equal to the mean, so this is the mean of your data. When you put that in the equation, you get 0. So you can see that brings the mean from your normal distribution into 0, which is the mean for the standard distribution. What if you go one standard deviation above the mean? Okay, so you're going to let y equal mu plus sigma. Well, put that in the equation. Obviously, these cancel off, and these cancel. You get 1. One standard deviation below the mean is -1. 2 standard deviations above the mean in your data becomes a z-score of 2. Of course, course, we want to look at arbitrary values, so um, that's what we're going to do in the next slide. Earlier there was an example of some normally distributed data for systolic blood pressure in a study, and the mean was 120, the standard deviation was 10. So you wanted to find the probability that a systolic blood pressure was between 112 and 130. Okay, these are arbitrary values. Before, we looked at the probability and the percent of the values that were between uh, the mean and a certain number of standard deviations. Now we're just going to look at arbitrary values. So the procedure here is to take these arbitrary values and put them into z-scores. So the 112 becomes a z-score of minus 0.8, and the other value, the z2, becomes 1 because it's a standard deviation above the mean. Remember, the mean was 120 and the standard deviation was 10. So now we've transferred those into z-scores. We now can use the tables, the z-tables. Okay, so now I have to make a remark on the statistics tables in the back of the textbook, the Mendenhall textbook. You have to be very careful when you use tables. Look at the headings at the top and see what they're actually giving you. They don't always give you the same thing. And I'm going to discuss here how to use the tables in Mendenhall because that's the book we have, but which is a good book in other regards, but those tables aren't typical. Right. So what the table is giving, I'm going to draw a picture of it here. So here will be these are my z values, and here's my standard normal distribution. Okay, what the table gives is the area between 0, get a different color. Okay. Between 0 and some value z1. So you look up the z1 and it's giving you this area. Alright? Remember that. Everything else we do, you're just going to add and subtract using the idea that that's all you've got, is that area. Most statistics tables give you the area from this z1 all the way down to negative infinity. Of course, all you have to do is add 0.5 to that value and you would have it. So, but that's typically what you get, and R is going to give you something similar. So when you put the Z1 value in, you're going to get everything south of it, all that entire area there. And so our problem was to find the probability that the z-score was between minus 0.8 and 1.0. Right, since you don't have this area right here, I don't think I can erase it. I'll just have to do it over again. Let me draw it. Let me just erase that. And I'm going to draw again what you have. And the table's in the back. For the Z1 that you look up in the table, you get this area right here. Okay. So we're going to have to break this into two parts. We break it into the first one, which is going to be the area between that z lies between 0 and 1. So in that case, this will be 1. So we get this area. For the other piece, we look at the probability that the area is between minus 0.8 and 0. Well, from the table, the first one is that 34%, so you get 0.3413. Okay, so this area is 0.3413 in the table. Now, you need the other one, which is down here at minus 0.8. By symmetry, this area is the same as the area from 0 to positive 0.8, right? By symmetry, this area here is the same. I'll do it in red over here as that. So since it's the same area, you can take the probability that the value lies between minus 0.8 and 0 is the same as the probability that the value lies between 0 and 0.8, which is 0.2881. So I know that this area by symmetry and by the table is 0.2881. You add those together and you get about 30 some percent or 60 some percent, and that's the probability. And you see you had to break it into two pieces. When I show you how to do it in R, you'll see it's much simpler than this. And here's a graph of what we get. So the probability that the blood pressure was between 112 and 130 in that previous study is the same as the probability that the z-score lies between minus 0.8 and 1, and you have to break it into two pieces because that's how the table goes. So the upper piece was 0.3413, the other piece was 0.2881, you got about 63%, and that would be the area here shaded in this graph. And this works for all normal distributions because the transformation from the y to the z-score depends on the mean and the standard deviation for that particular data. So let's look at how to do another type of problem. So we want the probability that z is less than or equal to 1.67. All right. In the tables, all you have is this area. You can look that up. So this is your 1.87. But then you have to add to it this area, and this area is 0.5. That's in your homework somewhere. What is the probability that the probability that any value is less than or equal to the mean? It's 0.5. So then you have to add that to this area. So you'd add these two areas together to get this total area. In other statistics tables, you just start with this value and the table gives you this value. Now what if you want to find the value, the probability that z is greater than? So I'm looking for the probability that z is greater than or equal to 1.87 instead of less than. The way to do that is to find the probability, this probability over here, and then subtract it from 1. So it's 1 minus the probability that z is less than or equal to 1.87. Okay, now I'm going to show you how to do the problem using R. Let's remember first a difference between the discrete probability distribution and the continuous. For the discrete probability distribution, so I'll draw one here. Okay, it might look something like this. Whoops, I grabbed this side there. So this is your probability, and these were your y values, your discrete y values. Right. For the discrete probability distribution, you can find the probability, let's say this value is 1, 2, 3, 4. Okay, you can find exactly that the probability that y is that particular value 1. Right? In fact, it's given right here. And in R, you just use D. I forgot which way D goes. Okay, D binom, and you gave it this value. All right. So here's your binomial probability distribution. You had to give it your parameters, of course, and all you used was D, which was these points. Sometimes we wanted to know the probability that it was, say, less than 3, in which case we would have had to add these numbers up here, but P binom did that automatically for us. Okay. Now that we come to the continuous probability distribution, things are a little bit different. So I'll just sketch one here so you can kind of see it before we start. Okay, here's one. I'll use z values here. So this is not the probability, but the probability density. Okay, here's my z values. Can I find the probability that Z has a particular value, say Z1? No, because I would be looking for the area, and what would that area be anyway? It'd be 0. At one point, it'd be 0, so you can't find that. All you can find is that it's less than or greater than. You can't find it exactly. This is no good. So keep that in mind. So when we did the binomial and the Poisson distributions, we could use D to find an exact value. And then we use the P binom or P Poisson or POIS to find whether it was less than or greater than. But remember, all it was doing was adding up these numbers right at the top of this curve. Here we're looking at the area under the curve, and we never find one particular value. I like to put that on tests or homework. Okay, so now we're back and we're in R now. And I want to find the value that Z is less than something. I can't write that in very well, but we'll just say um, probability of Z less than, it doesn't like symbols over here too well, less than, well, let's say 0, because that's the mean. Well, for that, I use the P, probability of the normal distribution. There's a tutorial on this, but I'm just going to give some of the commands here. And we'll just put a 0 here. Well, I can just do it that way. I can give it a name, or let me just write it out, because all I want to do is show the values. 0.5. Well, yes, the probability that a Z value is less than the mean of 0 is going to be 0.5 because of the symmetry of the curve. Okay, I can do the same for any other probability that the normal is less than 1. Okay, there's your answer right there. All right, what is done, it's all the work that you had to do in the tables, it does it for you automatically, and what it's giving you is either less than or greater than. The default is less than. If I want to find the probability that Z is greater than 1, okay, then I just say lower tail equals false. Lower tail equals true is the default, and so now I get the other values. So all I've achieved here, okay, it's a good idea to sketch this for yourself. And all problems in science and engineering and a lot in math are readily solved by sketches. Okay, so for this case, I wanted the probability that Z was less than 1. Here's 1 right here. So when I put that in, I just got this value right away. Now when I say lower tail, obviously this is a lower tail here, I say lower tail is false. I've mixed up my color scheme. Blue. I got this value, and I got it automatically by just writing lower tail equals false. Right, that's fine if you have Z values. What happens if you have arbitrary values? Well, you can change them into Z values, and there's some commands for that. You can do it with arithmetic, or you can do it with a scale. There's an R command called scale that does it automatically. Or for the normal distribution, pnorm will do it automatically. You just have to tell it what the mean and the standard deviation for the data. You have to give it those parameters. So for example, let me get the cursor back here. I think I'm back. There we go. Okay, P norm. And let's say for that blood pressure, we want to find, well, it'd be equivalent to this. Let's say that blood pressure, what's the probability that blood pressure is less than 130 when the mean is 120 and the standard deviation is 10. Okay, in other words, let's look, what is the probability that the blood pressure is less than or equal to 1 standard deviation above the mean? That's the same as Z equal 1, and we better see the same value, and we do. And you can do the same thing here. Let's do up arrow, and I'll go in here and put lower dot tail equals false. Okay, so we got the same values. All right, when you're given these less thans, what happens if you want, I'll draw this here. Okay, so here will be a distribution, and I'll just draw it in Z. It's just as easy to draw it in Z. So the problem we want to consider is that we want the probability between two Z values. We'll call this one Z1 and this one Z2. And it was done a little bit differently in the Mendenhall tables, but here's what you do for R and for most statistics tables. You find the probability that the value is less than Z1, and then you find the probability that it's less than Z2, and you subtract them, and that will give you good green. That will give you this probability in here. Okay, so here's how that's going to look in the Z commands, in the R commands, sorry. Okay, so I take the probability, and you can give it all the parameters you want. Let's say I want the probability that the blood pressure is between 130 and 112, whatever we did before. So you do the 130 first, give it the mean of 120, standard deviation of 10, and you want to keep the lower tail, and that's the default, so you don't have to say anything. And you subtract from that. Well, it looks like I made a mistake there, but I can fix it. 112. Again, you have to tell it the mean of 120 and the standard deviation of 10. Okay, remember this is R, so all you have to do is go back here with your back arrow, and I didn't mean P, I had to say norm because I had to tell it the distribution. So now I've just subtracted those two areas. Great. Oh, okay, that's okay. You're going to make mistakes too. It's not a big deal. Hit the up arrow, space over, and you see I put a plus sign here instead of an equal sign, and now we get a value. Remember, it was about 63% when we calculated it using the tables, and it's still 63%. Again, there's these commands are also in the tutorial for R.